Hello, and welcome to Field Lab Earth, the podcast that's all about past and present advances in the fields of agronomic, crop, soil, and environmental sciences. Today, we'll be talking to Dr. Tyson Ochsner. Field-scale soil moisture measurements can be difficult to attain, point-scale data can be too small to give field-scale advice, and data gathered from satellites often lack important specificity. In this episode, Tyson joins me to discuss a new method to scale point data into field-scale soil moisture measurements. We'll talk more about that in a minute, but before we dive in, we wanted to thank our sponsor for this episode, EA Consumables. EA Consumables is the exclusive U.S. distributor of organic elemental analysis products by UK laboratory supplies manufacturer Elemental Microanalysis. Visit eaconsumables.com for high-quality elemental analysis consumable supplies that offer performance you can trust. I'm your host, Abby Morrison. Let's talk about science. Hi, everyone, and welcome to the show. Today we are talking to Dr. Ochsner. Dr. Ochsner was raised on a farm near Chattanooga, Oklahoma. He earned a bachelor's in environmental science at Oklahoma State University in 1998. He then studied soil science and water resources at Iowa State University, earning a master's in 2000 and a PhD in 2003. From 2003 through 2008, he worked as a soil scientist for the USDA Agricultural Research Service in St. Paul, Minnesota. Since then, he has served as Assistant Associate and Full Professor of Applied Soil Physics in the Department of Plant and Soil Sciences at Oklahoma State University. Hello, Tyson. Welcome to the show. How are you doing today?
I'm good, Abby. Thanks for having me on.
Yeah, we are so glad to have you. So today we are talking about some new techniques to try to get field scale data for soil moisture. So to get us started, can you just talk a little bit about kind of where field scale data falls within the different kinds of data that you can have, why it's helpful to have it, and also why it's kind of hard to get and why we need some better techniques?
Right. Yeah, happy to. So field scale data falls right in the gap, I would say. It falls in the gap between the kind of measurements that we can typically make on the ground, which are usually point scale measurements. You know, if I go out with a shovel and collect some soil moisture and take it to an oven and dry it, I can determine the soil moisture that way, but it's just for that one point. Or if I take a sensor and I, put the sensor into the soil and get a reading from the sensor, that's great. But it's just going to represent that single point. Usually people who are interested in soil moisture, whether they're a farmer or whether they're studying water resources, or maybe they're an ecologist, lots of different people are interested in this. They're usually interested in more than a single point, and if they're involved in land management, they often are going to want to know the soil moisture conditions at the scale at which the land is managed, which is usually what we would call the field scale. So they might then think, well, my point measurement is too small. I need something at the field scale. So let's go to a satellite. And maybe a satellite will be able to give us field scale soil moisture. But unfortunately, that's usually not the case either. So the best soil moisture satellites are using a technology that measures over very large areas. So the signal that they're getting is coming from an area of about, 20 miles by 20 miles on the ground, or 36 by 36 kilometers, something like that. And so it's a big area that's producing this signal that the satellite sees. We have a lot of great science and research that tries to make that more detailed, what we call higher spatial resolution, and to get down to smaller scales. But honestly, those things are still very much a work in progress right now. And the best ones are still getting just down to a few kilometers or something like that. And we're usually managing fields that are smaller. Some people might, in the U.S., we have this quarter sections, like a half mile by half mile. Or 800 meters by 800 meters, or smaller in many cases. these are the sizes of our fields that we manage, and we need soil moisture information at that scale. That's what we're usually lacking.
Sure. Yeah. So quite the conundrum to kind of find that middle ground.
Yeah.
So before we dive into some of the methods, there is a specific piece of technology that you used in your research, which I will admit was one of the first things that drew me to this paper because it just sounds super cool and sci-fi. And I'm a big nerd, but it's called a cosmic ray neutron rover. So I'm hoping you can just give some definition to not only some of the individual kind of words that are going into that, but also the rover itself, what it looks like, how you use it. I would love more information on that.
Yeah, it's a really cool technology, so I'll be happy to unpack it a little bit. And it starts with this sort of far out idea of cosmic rays, right? So it sounds like something that Marvin the Martian would use or something.
Sure.
So cosmic rays are high energy particles, usually protons, that are coming in from outer space. They're coming into the Earth's atmosphere all the time, and they travel at very, very high speeds. And so that's what a cosmic ray is, these particles that are coming into the Earth at very high speeds. And as they come in, they collide with molecules in the atmosphere. And when they do that, they may knock something loose out of the molecule, out of the nucleus of the molecule. And what they knock loose is often a neutron. Okay. And so I've already said a couple other terms. So proton, that's a subatomic particle that has a mass of 1 and a charge of 1. A neutron is a subatomic particle that has a mass of 1 but a charge of 0. So it's uncharged. It has no electrical charge on it, but it does have mass. And so it gets knocked out by the cosmic ray, and then it starts to travel at a very high speed down through the atmosphere towards the Earth's surface. And the neutron may also hit another molecule and knock another neutron out. And so you end up with this, like a waterfall, if you would, of these neutrons coming down towards the Earth's surface, and they're moving at a very high rate of speed. So we talk about these neutrons with different energy levels. And so I'll name 2 that are the ends of the spectrum, and then we'll talk about the middle. So the fast ones, thankfully, are called fast neutrons. So that's a simple term. We can understand, okay, these are the ones that are moving really fast. They're moving at like 30 million miles an hour. So these things are cooking. The slower ones, the slowest ones, they're called slow neutrons, and they move at about 5,000 miles per hour, which still sounds incredibly fast, but not compared to the fast neutrons. So the fast neutrons are the really high speed. The slow, or sometimes we say thermal neutrons, are these ones that are moving at like 5,000 miles an hour. And in between those two, there's another kind of neutron that's called epithermal, which means epi is like your skin. It means like what covers you or what's close to you. And so just close to the thermal neutrons are the epithermal neutrons. They're moving a little bit faster. And those are the ones that we want to measure with the rover.
I'm curious as to what this rover looks like, because I tried to look it up because I think a lot of people would be like, oh, like a moon rover. And it's not really like that. But that would probably be the easiest like mental tie that I would have by default. But also it's interesting how I'm curious how measuring those cosmic ray neutrons would translate into how much moisture is in a field. So I'm hoping you can expand on both of those.
I will try. Yeah. So I didn't send you don't need a picture of the rover to imagine it. It's just 2 big white metal boxes. So it's very nondescript. It looks like your junior high locker, painted white and laid on its side. I mean, it's just a big white metal box. But inside is where the magic happens. So inside the 2, our rover that we're using has 2 of these big white boxes, and inside each of the big white boxes there's 2 stainless steel cylinders. Okay, so for a total of 4 cylinders, and each of those cylinders is filled with a certain type of helium gas. And so that helium gas interacts with the neutrons when they come into the tube. These neutrons are passing through, me and you and the soil and the metal. They don't care. They just go right through. And so they come into that stainless steel tube, and there's a high voltage wire in the middle. And so as the neutrons pass through, they interact with the helium gas, and they make a little voltage spike on that wire. And so that's what we actually detect, are these little voltage spike. And every time we get a voltage pulse, we know that a neutron has just come into our tube. So so they're big neutron counters, basically. And so here's the interesting thing. These counters are constructed in such a way that they are really mostly counting these epithermal neutrons, these ones that are in between the thermal and the fast. These epithermal neutrons at the ground surface are an indicator of soil moisture. And I'll try to explain why that is. But basically, the more of these epithermal neutrons you have right above the land surface, the less soil moisture you have in general. And as the neutron counts go down, that means the soil moisture has gone up. And so and the cool thing about it, because these neutrons are traveling so fast, it's not just measuring the immediate point where the rover is sitting. It's measuring integrated measure of the soil moisture over the surrounding 100 or 200 yards in any direction, or 100 or 200 meters for our international listeners. So it's this integrated measure of the soil moisture conditions in the landscape.
I'm so thrilled. I knew this would be just a really fun one to do. So, and it is proving to be exactly that. So this is very exciting for me. So I have some follow-up questions on this. So these neutrons, they just hit the earth and they just keep on tunneling through, or do they hang out on the surface, bounce off, and then they just hang out there? That's first question.
Yeah. They keep moving.
Okay.
But so let me explain it. Yeah, it's a great question. So the fast ones are coming down, and the one thing that is most effective at slowing these neutrons down is a hydrogen atom. Because if you remember their periodic table, go back to junior high again, then your periodic table, the first element is hydrogen, because it has a mass of 1. And so it weighs the same as the neutron. And so it's a little bit like a billiard ball or pool ball effect. And so, when you strike the cue ball and it's going along pretty fast and it hits another ball, that ball takes off at a higher speed and the cue ball slows down. Same thing with a neutron. When it hits a hydrogen atom, the hydrogen atom picks up some of that energy and the neutron slows down. Now, if it hits so every time it hits a hydrogen atom, it actually loses half of its energy. And so the more hydrogen it's hitting, the more it's going to slow down. And the main source of hydrogen, if we're out on the landscape, is usually the soil water content, right? So hydrogen, H2O, that's the main source of hydrogen in the landscape. And so the more of the soil water there is, the more those neutrons are going to get slowed down. So they're actually going down into the soil, interacting with the soil and the water. Some of them are coming back out, and that some of them are epithermal neutrons now because they've been slowed down some by that water down below the ground. Some of them actually will go down there and they'll interact with so much hydrogen that they become thermal neutrons, and they may not come back out of the soil. They may sort of get stuck down there. That's the idea. So those epithermal neutrons, they've interacted with the soil. They're also interacting with the vegetation, which also contains water and can also slow them down to some extent. So sometimes we have to correct the data if we have a large amount of vegetation present. That can be another important pool of water that we need to account for.
Oh man, I love this. Okay, so then that's actually a great addition, because I think it'll help kind of transition us from my next question then into our methods, which is When you're using this rover, are you just towing it along in a trailer? Is it just in the back of a truck or a van? And then are you just driving over the field in order to get those measurements?
Right. For this study that we're talking about today, we put it in the back of a what they call a UTV, or they call a side-by-side. Basically, it's a small off-road vehicle. And so we just loaded the 2 boxes of the rover and the little data logger into the vehicle and just drove, back and forth around this pasture and rangeland where we were working so that we could monitor and those neutron counts there at the field scale. And we were able to convert those into a good estimate of the average soil moisture for this field. So, which was about, again, 800 meters, or about, half mile, quarter section.
Okay.
Yeah.
Perfect.
So we're just driving it. You can put it in a truck and drive it down, ideally, down dirt roads, preferably. And we do that also to make maps for larger areas. If we want to try to make a map of a watershed or something like that, we can also use it that way. But in this study, we're really focused on this one particular field to really get detailed information.
Hi, everyone. I hope you're enjoying the show. Interested in learning more? Tyson's paper, Upscaling Soil Moisture from Point Scale to Field Scale Towards a General Model, published in Vado's own journal, is always freely available. If you are a certified crop advisor or certified professional soil scientist, you can take a quiz for continuing education units for this episode, which can be found in our show notes or on certifiedcropadvisor.org. Thanks again also to our sponsor, EA Consumables. What kind of soil standards does your lab need? Loamy, clay, peaty, chalky, silty? EA Consumables has a new line of synthetic soil standards from Elemental Microanalysis, which offer superior consistency between batches for improved analysis results. These synthetic soil standards are made from pure mineral and chemical ingredients. Visit eaconsumables.com for more information. Thank you for being our sponsor. Let's get back to the show. Zooming then out, as I have zoomed us in tremendously close, can you just describe on a high level then the specific goals for this research project and just more information about the methods of how you went about planning this and implementing this project?
Yes. Yeah. So I'll loop back to the scale gap that we talked about earlier, that we have some good ways to make point measurements of soil moisture. We have some satellites that can measure soil moisture for sort of very large areas, but we often are lacking good information at the field scale. That's this gap that we're often trying to address. And we usually don't have a cosmic ray neutron rover, right? Those are very unique instruments. Most people don't have that. And so we need some way, in this research, we're looking for some way to upscale the point measurements to the field scale. And so I'm kind of throwing out another term there. We talk about upscaling. It's the idea of establishing a relationship between the soil moisture that we're measuring at one particular place in the field, relating that to the average of the field. So that moving forward, if all we have is information at that one point, we can still effectively estimate the average for our field that we're interested in. That's what we mean in this context by upscaling. So the objective of this work then was to try to develop an upscaling method that could be, broadly applicable to these point scale in situ measurements that people often have. So for example, we have in the state of Oklahoma about 120 places around the state where we monitor soil moisture at a point scale in our long-term weather stations. So that's great information, but each one of those only represents the conditions right at that station. They don't even represent, the field necessarily that's around them, much less other fields in the area. So that there's a need to upscale from those point observations to these fields. Likewise, around the world, there are thousands of places where people are making point measurements of soil moisture conditions. That's great, but we often want to know what is that single point measurement telling us about the field or the larger landscape around it. And so there have been some people who developed upscaling methods before, but they've mostly been sort of one-off type of things. Like they had a particular study area and they developed a specific relationship for that particular area, but it's likely that those are not going to be applicable as we move to other places. So we wanted to try to find a way to develop something that was more broadly applicable so we could upscale all the soil moisture stations in Oklahoma, or perhaps all of them nationwide down the road. That's the goal that we're working toward.
Sure. I have 2 questions off of this. I'm going to ask both of them now, so I hopefully don't forget. And we can,
Great.
If we need to go back to repeat it, we can figure out a way to do that. So my first question, the easier one, is probably going to be like, how many point measurements do you need for this to work? Because obviously you can have anything from, I'm going to go dig a hole and get some soil to test. And you can have like an environmental station, that's getting that much broader perspective. So when you're looking at this, like what level of or frequency of point measurement are you comparing this to? I will cut off there. Just ask that one first, actually.
Okay. When we think about upscaling, we are usually going out at some specific snapshot, some specific moments in time, and gathering in some way an accurate measure of the field scale average that we want to know, and then also pulling out at that specific time some of the point scale data and looking at the relationship between the two. So, if we only do that once, it's not going to be a very strong relationship. So the more times we can repeat that, we can develop an upscaling method that covers, a broad range of soil moisture conditions. It's something that should work when it's really dry and still work when it's really wet, hopefully would be the goal. So in this study, we went out, with the rover numerous times, over the course of about a year, going out and taking these measurements roughly on a monthly basis so that we could see, seasonally and when it's dry and when it's wet, what do these relationships look? Once you've developed the relationship, if it's working like it should, then you can take the detailed time series of data from that point measurement. Let's say you have a sensor and it's giving you a value for that single point every day. Then you apply your upscaling relationship to that, and then you get a value for the field average every day. And so that's the goal, so that you need, a pretty good data set to develop the relationship. And then once you develop it, if it's working properly, you can apply that sort of every day moving forward.
Sure. And how many of these little point sensors would you need in a field for? Because obviously if you're just like in one point, that's probably not going to actually help you that much. How many of those would you need?
So that's a great question. So if we want to use point observations to represent the field average, we may need a significant number, and so that people have estimated that number, and it kind of varies depending on how accurate do you have to be and how variable is your field. But, roughly 15 to 30 would be kind of the typical kind of range that you would think about. If I'm a farmer trying to manage irrigation or something, that's probably not practical for me. I'm probably not going to put 15 or 30 sensors out in my field that I have to work around and try not to hit with my farm equipment. And then the cost of doing that is it's not very practical. So we're looking for a way that you can have a single sensor, just one point in the field that you monitor, and then you have this upscaling relationship that lets you estimate the average based on just that one single station. And so the unique thing of this study is we were able to develop that relationship by using that cosmic ray neutron rover. That rover gives us a really nice field average without having to put 30 or 40 or 50 stations out there to monitor the field average. So that was really the key to this study is having that rover technology.
Sure. Oh man, I love that. That makes me so happy. It's interesting you mentioned that because one of the things I was thinking about, which was actually my other second question before I slipped in a different second question, was about kind of the relationship with a project like this to something like precision agriculture. Because I know there's a lot of just research being done on trying to get a lot of that point scale information so that you can really moderate what you need to at different levels for, nutrients or moisture or what have you. And so it's interesting to have a project that is not trying to like really narrow down into the weeds, pardon my pun, sort of, maybe, to kind of get something that is much more on that field scale. So I was hoping you could just talk about kind of the relationship between those two different kinds of data sets and approaches to farming and how they interface. Obviously, not wanting a bunch of sensors in your field is one factor of that, but how else do those relate?
It's a great question. Then we think about precision ag, often we're thinking about trying to get data at higher and higher spatial resolutions so that we can do things like maybe variable rate irrigation, or maybe we want to do variable rate nutrient applications across the field by having sort of very detailed maps of what's happening in the soil, what's happening with the crops. And that's a worthy goal. That's a good goal. And some people do that. But by and large, most agriculture around the world is managed at the field scale. So it's just the reality of where we are. There's a lot of reasons why that's the case. Even though these variable rate things have been available for, a few decades now, they're still not the normal way that agriculture is managed. So most agriculture is managed at the field scale, and the precision is being precise in doing the right operations at the right time. That's where the precision often comes in. It doesn't necessarily come in by dividing up the field into ever smaller units. That sometimes doesn't have enough payoff to make it worthwhile.
Yeah.
So just kind of two different, approaches to management. They both have their value in certain places and certain times.
Yeah. I love this because it's very much like two different types of good that are both doing wonderful things to help people to survive and thrive. And so that makes me really happy that it's kind of this partnership where you have researchers kind of side by side approaching important issues from multiple angles, which is what we need. The more tools in the toolkit, the better.
Absolutely. And I think as we continue to move forward with this type of research, we'll learn cool ways to cross over between those different philosophies and different approaches to management. So
this is just filling my heart. Very, very excited to be having this conversation. We've talked a little bit about kind of how you went about this, of kind of taking your rover over the field to collect your data, comparing that to some of the point scale data that you were getting to find this relationship. Tell me what you found. What factors impacted the model, and did it work?
Yeah, absolutely. So yes, it did work.
Great.
So far, I mean, we have a lot more work to do, but so far, so good. We wanted to evaluate different, types of inputs that we might use in an upscaling function to be able to estimate, from that single point in the field, what's happening with the field average. And so there's some logical things to consider. We would want to consider the soil textures and how they vary across the field. We know that's important to soil moisture conditions. We would want to consider topography, and how the slopes and everything in the landscape positions and how they vary across the field. And we would want to consider differences in the vegetation. Obviously, vegetation has an impact on soil moisture. And so we want to consider how that varies across the field also. So we brought in those three in particular as potential inputs to our model. So we looked at, the sand content, at 30-meter resolution map across the field. Clay content, I had 30-meter digital soil map for clay content as well. We looked at elevation. We had an even higher resolution map of the elevation of the field. And we looked at a vegetation index that's called the Normalized Difference Vegetation Index, NDVI. It's a very common vegetation index. And so we pulled in all of those data and we looked at, okay, if we know those values for our specific point where we're measuring, and we know the soil moisture for that point, which of those helps us predict the soil moisture average for the field, which we had determined with the rover. And what we learned, somewhat to our surprise, was for these conditions and this for this field, the only thing we really needed to know was the sand content. So that was the factor that had the most significant influence. If we knew the soil moisture measured at our single monitoring point, and we knew the sand content, both at that monitoring point and how it varied across the whole field, then we could estimate the field average with pretty good precision.
Wow, that's amazing. So when you're driving your rover around, are there crops that are getting crushed at this point by this rover, or are they fine?
Thanks. Yeah, I didn't say anything about the type of site. Thanks for bringing that up. This site was all, it's a grassland site. It's used for cattle grazing. And so it's warm season grasses there, native grasses, big blue stem, little blue stem, some of these wonderful prairie grasses that we have here in Oklahoma. And so, and then there's also, there are some trees, some oak trees, some eastern red cedar trees at this site, but mostly grassland vegetation. There's quite a bit of topography on this site. So there are old terraces from when it used to be farmed. So, and then there's a sort of a little creek that runs down through the site. And so, so think of a grassland with like rolling hills, and the soil textures and types are pretty highly variable. So it made it a really nice sort of challenging test site.
Man, I love the idea of being like, I'm doing science, and the way that I do it is by like off-roading in a beautiful field for a day. I love when science is great.
When I go to, usually I'm stuck in the office and my students are out doing field work. When I get to go out and do field work with the students, I always tell them, wow, this is like a vacation.
Yeah. Oh man, what a fun way to do field research. That sounds great. Very idyllic. So the other fun thing about this that I appreciate is you can see even here with some of your modeling, you're bringing in some of that precision agriculture of knowing some of that variability. So even here, we're seeing some of that crossover. So that was really interesting to me, because I was thinking, what if you have something that's, if you have a sensor that's in kind of the part of your field that always gets flooded and it's been rainy, obviously there's going to be a lot of soil moisture, and how would that compare to, if it's on the top of a hill or something like that. So I like that your modeling is bringing in some of that, partnering with Precision Ag already in that area.
Yeah.
Well, gosh, that's amazing that you kind of narrowed it down.
Respond to that in that it is, for this to develop this kind of upscaling function, it was really important for us to have that detailed kind of spatial information that we were able to get, Landsat 8 data, which gives us the NDVI at a 30-meter resolution. That's really helpful. Likewise, we used a soil data set that comes from a digital soil mapping approach, and it also takes existing information and estimates the soil properties at every 30 meters. And so you need that. And you need also, when you put in one of your point station where you're going to be getting the measurements over time at that single point, you need to know the soil properties there. That's really important. So that detailed information, having those detailed inputs was really key in developing the upscaling function that we've developed. So absolutely.
Sure. Is that kind of information something that is relatively easy for farmers to have access to, or is that maybe a bit of a restriction to uptake on this?
So working with data like that can be challenging. The data we used are all publicly available, so that's not the limiting factor. But being available and being useful are two different things.
Sure.
Right? Yeah. So thankfully, there are, if we're thinking about, agriculture, there are an increasing number of businesses out there who are, working to take these kind of, the satellite NDVI products like we use, perhaps even the digital soil products like we used, and putting those into sort of apps or web interfaces that are geared for land managers, people who don't have time to sit at the computer and develop a computer program to process all of that data. And so to me, I think it is getting better. It is getting more accessible, but it's still not trivial usually. And a lot of times, if you want to have those, private companies provide that information, well, you're probably going to have to pay for that. So
yeah, no, that makes sense. Seems like a great step forward in trying to make these measurements easier to get to, and then being able to simplify what they actually need by kind of cutting out what elements are not actually that helpful through your research. So great link there. So that kind of links us pretty easily into my next question, which is all about future research. So where are we headed? What are the next steps?
Yeah, so this was really what I would consider for us to be a first step, towards having this sort of a general upscaling approach that we can apply around the world, hopefully someday. But right now we're starting kind of small. So we started with these, there were 6 different stations that we worked with in this study and developed an approach that worked well for all 6 of those. So that's great. Our next step would be to try to do it for about 100 stations across the state of Oklahoma. So to apply the model we've developed here and see how effective is it for upscaling soil moisture at all of the Oklahoma Mesonet sites across the state, which about 120. So that would be the next step. And as we do that, we'll likely learn more. We may find some ways to improve the model and so forth. And that's great. And we'll continue to develop that. And if we have the opportunity, then, we just continue from there and try to move out to a national scale. There's more than 1,000 soil moisture monitoring stations across the U.S. that we could apply this type of upscaling to.
Amazing. Very promising. This is great work. I'm excited to see where it goes in future. So I have already riddled this conversation with rabbit trails, so I will bring us to a close with the final 3 questions. So the first one is, if listeners want to learn more about anything that we've talked about today, where can they go to learn more?
Awesome. Well, I want to name 3 things if they're interested to learn more on soil moisture or all the things that interact with soil moisture. We do have a web page for visualizing soil moisture maps for the state of Oklahoma, and they're just pretty cool to look at. So everybody can look at those. soilmoisture.okstate.edu. Put the link in the show notes, but that's available. If you're a researcher, you can download the data from there and take a look at that as well for your research. But more broadly, just for anyone wanting to learn about soil and water, I have a textbook that's freely available online. It's called Rain or Shine. It's an introduction to soil physical properties and processes. And so that book is freely available online through the Open Science Framework. And then the last thing I want to mention is we have a YouTube channel. So if anybody is interested to learn about these kind of topics, check out our YouTube channel, which is the Oklahoma State University Soil Physics YouTube channel. So any of those things might be interesting for someone wanting to learn more.
Sure. We will definitely put links to all those in the show notes. And obviously, those are also action items in their own right. But what else can people do if they want to kind of take that next step to get involved, either in this research or trying to implement these kinds of things where they farm?
Yeah. So one thing to to look for is if you like to get involved in sort of monitoring what's happening around you, like soil moisture and otherwise, you can check out an initiative called CocoRaws, which is basically a citizen science approach for monitoring the weather and, in some cases, the soil. So that's a pretty cool effort, and anyone that's interested can apply to become a CocoRaws observer and contribute information from where you live to this growing national database. So that will be one cool thing for people to check out.
Awesome. Yeah, that sounds great. And what a fun name also. Big fan of that.
Yeah. I don't remember what the acronym stands for, but it's easy to say, CocoRaws.
Yeah, I like that a lot. Wonderful. All right. So final question then is, what is one fun fact that listeners wouldn't know about you if all they had was your research?
Well, one thing about me is I'm a family guy. My wife, Stephanie, and I have 6 children, and we are excited to soon become grandparents. So we're really looking forward to that.
Oh, yay. Congratulations. That's wonderful news.
Thank you. Yeah. First one is on the way this fall.
Oh, wonderful. Well, we are certainly ending on a high note for this episode. So thank you so much for your time and all of the hard work you're doing to help farmers and land managers and the like. So thank you so much for being on.
You're welcome, and thanks for your interest in our work and helping to spread the word.
Awesome. Hi, everyone, and welcome to our Student Spotlight, where we highlight the work of graduate and undergraduate society student members. Today, we'll be talking to Jazia. Welcome to the show. Can you start us off by introducing yourself and where you're studying?
I'm Jazia Jannat. I'm a PhD candidate in Crop and Soil Science Department at University of Georgia, and originally I'm from Bangladesh.
Awesome. And what are you currently researching?
I'm currently working on my PhD project based on quantifying the frequency of flash drought in the southeastern United States and estimating its effect on different crop yields, corn, cotton, and forage crops. And the project is funded by National Oceanic and Atmospheric Administration, and I'm working under Dr. George Validas. And the main objectives of my research are to quantify the incidence of flash drought in the southeastern United States using suite of smart irrigation apps, and also another objective is to observe the effects of flash drought on growth and yield of rain-fed corn, cotton, and forage grasses using crop modeling system.
Great. And if you could have your dream research project, what would that look like?
I really want to work on developing management practices to enhance soil health and crop production by maintaining water balance and soil nutrients based on using different applications of precision agriculture.
Awesome. Well, if you'd like to get in touch with Jazia, we'll have her contact information in our show notes. Thank you so much for being on the show today, and best wishes on your future studies and career. Thank you.
Thank you.
Thank you for listening to Field Lab Earth. More information can be found in the description below. Thank you.